All right, let's do this. Welcome to The Explainer, where today we're going to absolutely crush an entire chapter of physics. You ready? Let's go.
Yep, you heard that right. Got a physics final breathing down your neck? Or maybe you just want a lightning-fast refresher? Either way, you're in the right place. We're going to cover everything you need to know about sound in, like, 5 minutes. Let's do it.
Okay, so here's a weird one for you. A guitar? A buzzing bee? What could they possibly have in common? One's making music, the other's, well, it's just being a bee. But in the world of physics, they're basically doing the exact same thing to make that sound. Any guesses what that is?
Boom. It's that simple. One word, vibration. Every sound, and I mean every sound, from a tiny whisper to a massive thunderclap, it all starts with something moving. Something wiggling back and forth super fast. That's the key. That's the source of it all. If you don't have a vibration, you don't have sound. Period.
Okay, so that's our starting point, the spark. If it all begins with a vibration, then what is sound, fundamentally?
All right, get your highlighters out, because this is a big one for any test. The official textbook answer is that sound is a form of energy. Think of it just like heat or light. It's not a thing, it's not matter, it's energy that gets produced by that vibration and then travels. That's the core concept.
And this image here is the perfect way to picture what happens next. See that tuning fork vibrating? It's literally pushing and pulling the air molecules around it. It's kind of like dropping a stone in a pond and seeing the ripples spread out. Well, a vibration does the same thing to the air, creating this invisible ripple, and that ripple is the sound wave, starting its big adventure.
Okay, we've got a vibration. We've got a disturbance. So what happens now? How does that little ripple get from, say, a bell ringing over there all the way to your eardrum? Let's trace the path.
So as that vibrating thing, let's say our tuning fork, moves forward, it literally squishes the air particles together. This creates a tiny area of high pressure. We call that a compression. Then, when it moves back, it leaves a little gap behind it, an area of low pressure, and that's called a rarefaction. So sound is really just this chain reaction, a wave of squished up air followed by stretched out air moving through space.
Now this is super important, and it's something a lot of people get wrong. The actual bits of air aren't flying across the room and into your ear. I mean, that would just be wind, right? Think of it like this slinky. You push one end and you see the wave travel all the way to the other side. But each individual ring of the slinky doesn't move very far. It just bumps into the next one. That's exactly how sound works. The energy gets passed along, but the particles themselves just kind of jiggle in place.
And this kind of wave has a special name. You're definitely going to want to know this for the test. It's called a longitudinal wave. All that means is that the particles are wiggling back and forth in the same direction that the wave is traveling. Parallel to it, just like that slinky.
All right, so we've established sound as this invisible wave of pressure. So how on earth do we talk about it? How do we measure it? Well, we need to look at its blueprint, the anatomy of a sound wave.
And here it is. You've probably seen this exact drawing a million times in your textbook. This graph is just a picture of those pressure changes. So the high points, the peaks, that's where the air is all squished together, our compressions. And the low points, the valleys, that's where the air is all spread out, our rarefactions. It's just a way to visualize the invisible.
Okay, everybody listen up. This is probably the most common question you're going to get on sound. The difference between loudness and pitch. They are not the same thing. Here's the cheat sheet. Loudness is all about amplitude, how big the wave is. Pitch is all about frequency, how fast the wave is. Let's dig into that.
So, amplitude. This is pretty intuitive. It's basically how much energy is packed into the wave. Think about it. If you barely pluck a guitar string, you get a small vibration, a small wave, and a soft sound. But if you really whack it, you get a huge vibration, a big wave with a large amplitude, and a loud sound. More energy, bigger amplitude, louder sound. Easy. Now, frequency is about how often the waves are coming. It's measured in hertz, which just means waves per second. A big, floppy bass drum vibrates slowly. Its waves are really spread out. That's a low frequency, and we hear it as a low pitch, like boom. A tiny little flute vibrates super fast. Its waves are all bunched up together. That's a high frequency, and we hear it as a high pitch, like tweet.
And of course, there's a formula. You knew it was coming. This one is non-negotiable. You have to know it. The speed of the wave equals its wavelength times its frequency. Wavelength is just the distance from one peak to the next. So speed equals wavelength times frequency. You are almost guaranteed to see a problem that uses this.
Memorize it.
Okay, next chapter. We know what sound is. We know how it gets from point A to point B. But what happens when it runs into something, like a wall?
Well, it bounces, it reflects. Just like light bouncing off a mirror, sound waves bounce off surfaces. And when that bounce is clear enough that you hear it as a separate sound after the original, well, that's what we call an echo.
But you don't hear echoes all the time, right? And here's the cool reason why. Your brain actually has a tiny bit of audio lag. It holds on to a sound for about 1/10 of a second. So for you to hear a distinct echo, that reflected sound has to take longer than 0.1 seconds to get back to you. Otherwise, your brain just mushes it all together with the original sound. And that little time delay translates directly into a minimum distance. If you do the math, it works out that you need to be about 17.2 meters away from a wall to hear a clear echo. That's another one of those numbers that loves to pop up on physics tests, so maybe jot that down.
So we've talked a lot about sound, but we've really only been talking about the sounds that we can hear. Turns out our ears are actually pretty limited. There's a whole world of sound out there that we're completely deaf to. Let's look at the whole spectrum.
So, this chart lays it all out. That little slice in the middle, that's us. Humans can typically hear from 20 Hz up to about 20,000 Hz, or 20 kilohertz. Anything with a frequency lower than that is called infrasound, and anything with a frequency higher than that is ultrasound. And for us, both are totally silent.
But hey, just because we can't hear it doesn't mean it's not useful. Actually, it's the opposite. Ultrasound is a total game changer. We use its high-frequency waves for all sorts of amazing stuff, cleaning tiny, hard-to-reach machine parts, and of course, in medicine. Echocardiograms, those first baby pictures, that's all done with sound we can't even hear.
And check this out. This is a fantastic example from engineering. You can shoot ultrasound waves into a big block of metal. If everything's solid, the waves go right through. But if there's a tiny, invisible crack hidden inside, the waves will bounce off it and, bam, you've just found a potentially catastrophic flaw before it could cause a disaster. Pretty incredible.
Which brings us to a final, kind of mind-bending thought. We know that animals use these sounds we can't hear. Elephants use infrasound to talk to each other across miles. Bats use ultrasound to see in the dark. It really makes you stop and wonder, doesn't it? What else is going on all around us? What other conversations, what other warnings are filling the air completely silent to our ears? Anyway, something to chew on. Now go ace that final.